That's all this time. And there comes the guy who's the here's the scene.
Yeah. What will show up on the screen when it shows up. Yeah, it's filled.
Is there an adapter? So just share my.
So now if you unmute, yeah.
Unmute from here.
I
gonna pick up this microphone, right?
Oh yeah. This one. So yeah, with that, this should be already speaking.
Yeah.
And if we screen share the presentation, it should work fine. Let's see. All right, nice.
Okay, so if I go full screen here, should not
We need the chat on the screen.
yeah. We can go the chat as visible.
We can put the chat on screen.
Yeah.
Yeah, it will go in the corner.
That's not. It's not there.
It's not me. We
You know, because it needs to be streaming the whole
No, but I
thing.
think it's because that's not my screen.
Maybe
This screen. Yeah.
Okay, where it seems that you're right. Yep. Okay. All technical problems are sorted out. So it is my pleasure to chair this second session with GCM. And the first speaker is Carlos Zapata-Carratala from the Wolfram Institute, who will speak about hypergraph rewriting and higher-arity algebra. Please, Carlos.
Thank you very much. So thanks a lot for the opportunity. I just chatted with some of you, and I was saying that this is my entry into the community. I'm really coming from I hope to explain that I'm coming from a quite different background, and to me, rewriting was this sort of light bulb moment of like, we can do this now. I'm stuck with a few problems I want to explain. So yeah, I'm currently working at the Wolfram Institute, which is a thing that's not yet fully launched, and I'm also the founder and president of the Society for Multidisciplinary Fundamental Research. If you're curious about that, I'll talk later. And all the research that I'm going to be talking about and sort of the background motivations and the project I'm running are on this website, Higher-Arity.science. You can go a look if you're curious about the stuff I'm doing, and feel free to know. So my motivations. So I have two main motivations that I want to talk to you today. One is what I call ternary associativity or higher associativity in general. The other is higher network analysis. These two seem completely unrelated. One is very mathematical, it's very sort of coming from questions in pure mathematics and extension of Lie groups and physics. The other is about real world systems and microscopic systems that we understand well, have higher order interactions. So there's a very nice connection between the two. I want to explain that connection at the end of the formal for representation. So what is the question of ternary associativity? Well, if someone told you, you learn groups, you learn all kinds of binary algebra structures, learn mathematics, and someone poses you the question of what should be a ternary group or ternary associative operation. Well, everyone guesses it should be the axiom he's thinking about, because that's precisely the axiom. With two associative operations together, that's what they satisfy. Well, it turns out that there is, is this the right axiom? That's kind of the question. And it turns out that there's no satisfactory notion of ternary group. And this is something I was quite shocked to realize. I thought I would just go and see and find the textbooks written on higher order groups, and there aren't. And so this got me a bit curious. Okay, so why don't we have such a well-established notion of ternary group beyond binary objects? And the reason I say this is because people do have notions of ternary groups, but they turn out to be not good for the purpose that I will explain in a second. So the other context where people look at ternary operations is what they call cubic matrix algebras. So these are have different genealogies of origin, but they mostly coalesce into this structure that was identified in the 1990s called the Zapata-Carratala associative structure, which is this particular operation. So if you have a matrix, an array of scalars, so you have some value over a semi-ring, you can do the particular composition, which you can see is adding over one index in three different positions. But you can do other things. You can do, for example, called the Fisher reason that will become apparent in a second, where you just pairwise contract some indices in that way. Or you could do this triforce, and again, names will become clear in a moment, which is this particular operation. So the motivation for thinking about higher order groups or this high-arity groups or this sort of cubic matrix algebras is that people have identified the algebras that are higher-arity. And there's a fairly well-developed theory about them. But so we all know that the algebras correspond to B groups. It's like a very nice real construction. And the natural question is, okay, what corresponds to higher-arity algebras in this factorial correspondence? And the answer is unknown. Nobody knows, and not only we don't know, but we don't even have candidates for what things correspond to those. So that's a big mystery. And the shocking part is that when you try to construct these products, and there are many other products that you can construct, where you can enumerate them. There are a few, but not that many. It turns out that none of them are associated. In the naive sense that I presented, none of these products are associated. Okay, that's kind of interesting. So this is why I was saying that associativity is probably. Okay, so different motivation angle is higher order network analysis. So last week I was in Vienna in the NetSci conference, and there was a lot of talks about higher order systems, generalizing from graph models to hypergraph models, and all these kinds of things. And I sat down with many of the researchers working there, and the mathematicians, and the sort of people implementing algorithms and doing data analysis. And the vast majority of techniques are based on something that people call projection or order rejection, which basically takes a hypergraph and outputs a multigraph that essentially captures the sort of the pairwise high order connections. So in effect, they are reducing hypergraphs into multigraphs. So this is not so great. You're losing all this high order information. Okay, so these are the two motivating questions that I have. How do you understand this higher order associativity, and how do you do proper higher order analysis of higher order networks? So these two are intertwined and related, and as I will show in a second. So the key to understand the connection between these two questions is that you can, on the one hand, take a hypergraph and define what we call the adjacency hypermatrix, which is just a structured object in a formal sum of arrays of adjacency. So if you divide by order, for example, these undirected hypergraphs, you can just basically construct these arrays per order, and you can formal sum. That's what we call hypermatrix. The other aspect is that you can have your matrix operations, these cubic matrix operations, you can actually model them in terms of index adjacency. So what I mean by this is the following. So this is why I call this the fish paper. You can represent your arrays as edges and your indices as vertices. And these things basically model how you contract your indices, right? So this is what we call the fish operation for that reason. This is what we call the triforce operation for that reason. We play the Legend of Zelda video games. That's the triforce in that video game. And this is the Zapata-Carratala So basically, the realization that you can use hypergraphs to represent this index contraction patterns. Now, motif rewriting turns out to unify these two problems in a very efficient way, I think. I mean, I'm not an expert on this, but I think I can see that this is really a confluence of problems here. And so the basic story goes as follows. I'm sure many of you, this is sort of preschool material, but kindergarten material, but this is something I want to review. So my understanding is that you have some topological data, or you can go to some adjacency representation, but this is a naturally compositional object, and you have a lot of algebra theory behind, since for these kind of guys. So you can, as I say, define some algebraic story about this adjacency data, and then, for example, take the square, that you end up with some new algebra, new algebra. But actually, it turns out that you can do the same thing by just doing motif rewriting. Right? If you do a particular algorithm of motif rewriting, which in this case is you select this particular motif, it tells you which are the paths of length 2 in your graph, and you do this sort of cumulative hypergraph in the end, just keeping the results of your motifs, of the motif rewriting, you end up with exactly a graph whose adjacency matrix is the square of the adjacency matrix of the original. Anyway, the point is you can do hypergraph rewriting in the graph rewriting or algebra with the adjacency matrix to basically do the same thing. Okay, so that takes me to what I call the topology algebra rewriting sort of relation or correspondence between these objects, which you can basically, if you're thinking in terms of doing operations on this sort of objects, you can either have sort of a more topological representation or simply sort of symbolic data structure. You can have this more algebraic data structures, or you could have where you have algebraic operations, but you could have just motif rewriting that you apply on your objects. So to me, this is pointing that there's some equivalence going on around here, and I'm not sure what's going on. I'm sure somebody that has very strong ideas about this, and I want to learn from them. But that's something I noticed, and so what I do is I generalize this to hypergraphs. I see no particular reason not to go to hypergraphs, where you just generalize to hypergraphs, and then we have this corresponds. So this is the sort of phenomenological data that I'm working with. This is this anecdotal piece of data that that motivated me to sort of push in this direction and get into this community, which is the fact that if you learn the matrix product operation in high school, maybe, I always wondered what is the best justification for this formula, this formula we all learn at some point. You learn linear algebra and it is absolutely justified there, but I would say that's a fairly high-tech justification. You have to find bases and think about linearity and so on. I think it's much more easy to justify when you're just thinking of this as some motif pattern recognition in a network. We're basically asking for paths of length 2, as everyone knows in network theory. So if you take that point of view seriously, which I have never taken because as a physicist and mathematician, I have never really exposed myself to that particular theory until a year ago or so, then you realize that, okay, so if I take this motif and I define this particular adjacency condition, meaning you have two vertices and you declare that your middle index is an intermediary index, so you're going to sort of quantify over the existence of those middle ones, or you're going to add over all the possible motifs. What you end up with is a compositional structure that takes pairs of adjacency matrices and gives you another adjacency. So that's a binary associative algebra. That's the usual matrix algebra that we're all familiar with. But okay, what if you change the motif? Right? I mean, when you have this, it's not so clear what else you can do. But when you have the motif, it's very obvious that you can just generalize and take different motifs. So when you change your motif, you end up with all kinds of things. If you do this kind of generalization, you end up with something that's not close in the sense that you begin with a matrix of 2-index matrix and 3-index matrix. So obviously, you have some non-close separation. When you do this particular motif with this adjacency, you recover the so-called Thatcher associative structure, and it turns out to be non-associative. And if you take this fish motif, you end up with this formula, and you have again a ternary. I call them ternary algebras because they are close against 3-index matrices, giving you 3-index matrices, and you end up with something that we call a semi. So I want to summarize those things. You take the usual motif for graphs, you end up with matrix multiplication, which is associative. You do the Zapata-Carratala one, Everybody knows if this is associative or not. You don't know. There's some kind of higher order action that is satisfied there. But if you write this one here, you end up with the so-called semi-heap properties. So semi-heaps are algebras that were known in the beginning of the 20th century and were actually defined by Soviet mathematician in the 50s, in Russian, but it was translated as heap. And they basically satisfy this condition. So that condition has a twist. B and B are swapped. So that's not the associativity at the beginning. Okay, so what to do? Okay, so there's clearly some very strong connection between motif rewriting and algebras of higher-arity. And so, as a mathematician, what I like to do is to abstract maps and so let's try to define objects that push beyond this sort of concrete examples. So my proposal to this is chemoids, is what I'm calling chemoids. So this is actually this is going to be a fairly naive entry into a realm that people have formalized a lot, and I'm aware of this work. But I want to really communicate the sort of concept that I have in my mind of what I think this thing should be doing, and how I think these objects can answer or be sort of the framework for answering questions that I've alluded to. Okay, so what is a chemoid? So a chemoid is actually, you should have a category, your favorite definition of a category in mind. And what I'm going to try and do is to generalize directly the definition. You will see that this is fair to do, or it is a good thing to do, because we have many different examples of structures that are not typically considered as categories per se. They are studied with categorical methods, but never studied as categories per se, that fit this definition. So we begin with some collection of primitive elements. You should be thinking of your objects. I'm going to use a chemical analogy just because I think it helps communicate the sort of idea behind this notion. So bear with me, I'll explain why I'm using this chemical analogy. So atoms are your primitive elements, very intuitive atoms. Okay, atoms form bonds, right? So bonds are the data structures that you can build with your atoms. It could be ordered pairs, it could be cycles, it could be, you're familiar with combinatorial species, that's probably the theory that you want to use to formalize this. So you should be thinking of morphisms. In the case of categories, bonds are just directed edges between atoms, so effectively ordered pairs of atoms, or two atoms. Okay, so with bonds, you make up molecules. So molecules are just diagrams. So for me, these are going to be simple hypergraphs built from bonds. My definition of hypergraph is actually labeled hypergraphs that can trace the sort of data structure that go just. And so this is what typically you would call a diagram in category. So it's some finite diagrams, right? And then reactions. So reactions, you have your bonds, you have the molecules floating around, and these things interact via reactions. So by reaction, I mean hypergraph reactions. So for example, in the case of category, if you have your example in mind, this would be composition, which here's where the chemical analogy comes into place. So if you're familiar with the definition of a category, I learned it in a sort of more theoretic way, I guess, where you have sort of sets of forms, and you can compose them when the types align and so on. So the way I like to visualize this is that you have sort of a bunch of morphisms floating around. Imagine they are molecules, they're sort of two-atom molecules, right? And they have atoms that are labeled, or they have type of the objects, right? They are labeled with the objects. And the idea is that this is some kind of thermal bath, and if two morphisms happen to have one atom in which there's an ingoing arrow and an outgoing arrow, you can those two molecules react, and they give out another molecule that is again of the same form, and sort of the B atoms of both flies off, and the molecule flies. So this is kind of the reason why I have this chemical analogy in mind, because I want to think of all the possible combinations that are allowed by your reactions. So if you're in a category, that's the kind of reactions that I think that's semi-category. Okay, so but obviously we have much more than we are mathematicians. We are not just phenomenologists of some computational system. We are actually doing some form of quotienting by equivalent things, and we want redundancy of some expressions. So we impose some kind of action that in the case of categories would be associativity for composition. And what I'm mostly presenting here, my main slogan today, is that in this analogy, what I call the molecular integrity principle, which is just a phenomenon. I want to show you many examples of things that you're familiar with, and I want to show that you can abstract a principle that seems to be behind. Okay, so just bear with me. And I look forward to getting into the technicalities of this after the talk. I wanted this to be much more accessible and visual. Okay, so let's see a few of the structures that everyone's familiar with. A semi-category, a unar, which is the name I give, just the structure just has units, so just have identity arrows everywhere. A dagger, semi-hippoid, and a knot. So this is going to be very, very simple. And this is basically, I'm going to do what you do when you first learn category theory, which is sit down with your basic axioms, your basic definitions, and just play around with diagrams. Right? Okay, so let's begin with semi-category. So semi-category is a chemoid, meaning you have atoms floating around where you can compose exactly this way. 3 atoms, 2 bonds in this way, and you have another bond in that. So that's composition category, right? Okay, so as I said, things are labeled. So if you actually keep track of labels, then if you begin with this particular molecule, this 3-bond molecule, then you realize that if all the possible reactions take place, which is you're applying this rewrite philosophy or rewrite approach to the state, you end up with a final state that is that has a bonds labeled between the same pair of atoms labeled into different ways. Okay, so we all know that the associativity axiom, traditional category theory, tells us that actually those 2 bonds, therefore morphism categories, are the same. That's why you write down the axiom of associativity. Okay, that's one instance.
Sorry, yes. You see the labels as part of the structure or just to denote the box?
They are definitely part of the structure. So I'm keeping it very sparse and very clean, but as I said, you can get into all the details, everything's linked. So you know that this thing is because that thing, not that. So yeah, so what about a dagger? Okay, so a dagger just basically reverses otherwise this diagram wouldn't make sense, but it's the same labeling 1, 1, 1. Okay, so you have a dagger which basically just takes a bond and gives you another bond in the opposite direction. So if you go on and do all the possible rewritings from a very simple initial state, just a single bond, a single morphism, then you get F dagger, and then you get F dagger dagger, but now you found 2 bonds in the same direction, living on the same pair of atoms. So you're again prompted to assume this sort of nilpotency.
So sorry, here you on the right you add an arrow of opposite direction. Was it previously thought that was kind of replacement? Well,
no. So this is okay. It's technically I'm doing it additive here. So I'm doing the additive rewrite. Okay. Although so I'm doing the additive so that so the pattern I'm trying to point out here is that I begin with a simple diagram, simple hypergraph, and then I end up with a non-simple one, sort of skeletal and label. Okay, so that's another instance in which you can see this natural property of daggers, this sort of volatility property in that way. But we can also mix 2 reactions. In chemistry, you have some chemical species, and you have several ways they can react. So if they are together, your phenomenology, your sort of chemistry is different. So this is what happens, for example, when you put composition and daggers. So if you put composition and daggers together, again, I'm not assuming any axioms about composition or daggers. That's the whole point of the story. So I just take some clever initial state, in this case, it's just G in this way, and I try to do rewrite. And this is summarized obviously. This is one single step. It's actually more steps. But just to make the point, give the point across. So you see this side, I'm just composing F and G. You see the side, I'm just taking daggers. But eventually, I compose this again, and I end up with this diagram, which are same situation. You end up with this sort of anti-homomorphism. Again, more example. This is just a pattern I want to illustrate. Operas. So in operas, technically, you have a tower of rules that all look like kind of like this, where you have some kind of directed edges that distinguish sort of inputs and output. And so they are written this way. You have sort of an intermediary vertex where they meet as a dangling vertex there. And so if you take, for example, this initial condition as a labeled hypergraph, and you go on your rewriting, you end up with 2 differently labeled final states. And again, it's the usual operator associativity axiom. Okay, so all these are examples that are quite well understood and everyone knows about them. The one that was exciting for me is that we actually rediscovered semi-heaps, the ones that I mentioned that were sort of defined in the 50s, and you can count with your 2 hands the number of papers that have been written about them since. They're very poorly understood algebraic structures. They're becoming more popular in the last 5 years or so, but they're actually very, very obscure. So systemic equipoise can actually be implemented in infinitely many ways, but there are two very clear different ways of implementing it. You can either do this particular sort of non-flowing diagram rewriting. So you have 3 arrows, but one is flipped, just this kind of democratic flow. So if there are 2 arrows pointing in one direction, you end up flowing in that direction, right? And the other is the fish. The fish takes this, how many, 6 vertex hypergraph with 3 edges, and just rewrites sort of the outermost. Fine. So the funny thing is that if you take this long fish initial state, and you label, by the way, you label by tuples A, B, C, the order, so the anatomy of the fish, right? So you're keeping track A, B, and C in position 1, 2, 3. They are tail, body, and head, right? So, because these are otherwise undirected, just have to assume they have an internal structure. So if you do that, you just perform the rewriting, and you end up with the same situation where you have 3 edges living on the same set of vertices, and they all are labeled different. So if you, again, follow the same philosophy, you actually recover this semi-hypoid axis, right? That was identified in that literature. So to me, this was quite a nice realization, because this actually was one of the products that we had with the cubic matrices, and this gave me, the confidence that there's a pattern here that we should really exploit to search for higher order Higher-Arity. Okay. Yeah. Perfect. Perfect. So we are doing this sort of prototype of a computational system that actually does this in practice, these finite small computations with my colleague Marc at the Wolfram Institute. And I'm basically just going to go over these slides to show you that we can implement these rules symbolically to basically do with this particular implementation what I was showing more visually in those 100 nodes. So for example, we can do the category morphisms, we can do the dagger here combined with the morphisms, do the operads, the fish, and we can do, so this is just an image to show the larger things. This is the Zapata-Carratala method applied to some initial state, and everything. This level is actually a very uninteresting one. It's a triple product, so there's nothing interesting going on there. But yeah, that's basically this story. So the goal is, there is this pattern. We have a computational system that can implement it, and we are. So I am ready to go on exploring as long as the systematic way of scanning and enumerating possibilities. And so the question is, how do we proceed? What are the structures that we want to find? What are the sort of what patterns should we look for, and so on? I mean, we have identified this one pattern, the sort of the non-simplicity principle, that we begin with a simple diagram and a non-simple one, the skeletal hypergraph. There's something going on, and that seems to recover a lot of the interesting structures that are known. But there might be more actions like that. And so that's kind of the stage of the first. And of course, when I knew about the Greta seminar and the rewriting community, I thought, okay, this is the natural home for these questions. And I'm sure many of you know already some of these answers. So looking forward to discussions. Thank you very much.
One question. So your example diagram suggests, in terms of rewriting terminology, there's some kind of confluence problem.
Yes.
Is that true, or is it just by chance?
No. So exactly. So there is. Should have said the word. So point confluence is my mind. Yes, there's a very strong correlation with confluence. Absolutely. I mean, we know that it's confluence, but it's more than confluence because. So, for example, these are different because they have different labels. That's why different.
So maybe confluence modulo or something.
Yes. So there is confluence at the level of the skeletal hypergraphs. Yeah. So if you remove all labels, all these cases are confluent. Okay. Yeah. But if you look at the labels, then obviously they aren't confluent. But there's more than confluent. So for example, this example at the end here, it's clearly confluent, and usually it's quite clear. At the end, you have a single expression of a ternary pair of ternary products, right? this confluent diagram only represents the freedom you have to take operations in different orders. Right? You can operate this one, then the other one, then the three, or so all this confluent diagram only represents that freedom. It doesn't represent something like associativity, right? So we know that we've seen the pattern. That, thank you for your question, because we've seen the pattern that we get some interesting axioms when there is overlapping. So when you could say there's some kind of causal entanglement.
Sounds correct.
Yeah, exactly. There is some There's some overlapping of patterns. Yeah.
Question.
Okay, yes.
Okay, somebody else. Okay, good. But therefore, clearly, confluence on confluence depends on the original axioms that you have, the original equivalences that you impose. So
you don't impose any. That's the whole point. You don't impose any. So you only set up your.
For example, for the case the dagger, which is the thing, and that when you dagger twice, you get the same. Is something that you state as an axiom?
No, that's something you find.
It's just because you find the same drawing.
Exactly. So
you say I switch an arrow, I switch it again, it's the same drawing, therefore they are the same.
Yes. So exactly, that's the abstraction we're trying to do. We're saying,
but they don't have the same label because one is F and the other is F dagger.
Yes.
But
exactly. So yes. So let me make that point very clear. So we're trying this proposal of Chemoy is one where you have the same ingredients as a category, but with very general patterns, but you don't assume specific axioms, algebraic axioms, because those are unlabeled. What we say is that you might find some, because you're going to enforce this general principle of if you find a confluent, overlapping diagram that gives you different labelings for the same edge virtually, then you must equate those labels. So it's a way of declaring, it's a way of generalizing those axioms without declaring them. So you are not imposing the axioms, you're more finding them as a consequence of your labeling scheme. So that's the crucial difference. The crucial difference that we are trying to go sort of pre-axiomatic in the usual sense.
One problem is the fact that actually what you are dealing with are graphs, which have isomorphism. So depending on the way you draw them, then you might find addition. So you have to be careful.
Absolutely.
Two things could appear different, but actually to a suitable isomorphism, they could be overlapped. And in this case, it would be the same. So it's interesting.
Absolutely.
Quite original with respect to how the ground, I think, Hyper-Arity or confluence in this kind of. Any other question?
I'll be happy to discuss the breaks.
If not, and if there is body from the chat, I don't think so.
No.
Then I would like to thank the speaker again. The second speaker is Mackie from Sussex, from the University of Sussex. Sussex is the one.
Are you presenting from your own device or from the?
We present a joint work with Shinya, Sato, and Marc Thatcher about graph edit distance structure. Right. If we turn this.
Oh, that's not. No, I'm broken it. Now, of course, there's some problems. Sign. Or at least on this side.
Depends whom you ask.
For me, it's absolutely equivalent. For people from home, maybe
If I stand this, is it better?
Yeah,
It's got the impression that it's actually you think you don't need this. Okay, here we are. This guy. Thank you very much. So, good afternoon. So, thanks very for introducing. So, I'm Ian Mackie. This is joint work with Shinya, Sato, and Marc Thatcher, who's going to be giving one of the line talks later as well. So, the talk is about graph edit distance for interaction net rewrite. So, I want us to say a few general words about this to start off with. This is actually some work that's sort of in progress, and it's one of those bits of work that's probably never going to really get finished. And so we decided let's kind of write something up, and that might sort of help to sort of focus ideas, and maybe we get a bit of help, and that might move bits of it along. But what I want to say to begin with really is that so interaction nets are founded on linear logic, and one of the things that we have with linear logic, that it gives us this kind of refined notion of computation. Sorry, no, it's not a problem. So one of the things that we try to do with this linear logic foundation is to try to understand sort of decomposed computation a little bit. So interaction nets help us to do that, and it really takes advantage of some of those things that come from linear logic. But you don't need to know any linear logic to understand. And one of the things that it's been really successful for is for efficient implementations of the lambda calculus. And the reason why that it's very efficient, and not just the lambda calculus, but computation generally, is that it's exceptionally difficult, I'm going to say sort of impossible, to duplicate computation. So if you've got a rewrite system, that whatever rewrite strategy you decide to use for that, it's impossible to duplicate computation. I'll say a few things about that afterwards. I've got an example of what an interaction net can look like. This is one representing a lambda term. I might come back to this and just point out a couple of things later, but we're not going through that in any at all. But the main thing for us is that interaction nets have a couple of nice things. And the first thing is that matching is very simple. So one of the most difficult things in graph rewriting is matching. It's trying to find out where is the next red X or where is the left-hand side of the graph. That's something that's very simple in interaction nets, and I'll show you what that looks like in a minute. And the whole purpose of this work is how can we do those rewrite moves in the most efficient way possible. This isn't picking up. Yeah, that's good. Thank you. Okay, so went too far. So what I'm going to do is very quickly then to give a little bit of inspiration of what this work is about, and that's thinking about the edit distance from the Levenstein distance. So that's about editing text. What's the least number of operations that you can do to convert something into something else. So in that case, words, what we want to do, of course, is graphs. So a few words about interaction nets, and then I'll say a little bit about the approach that we took and some benchmark results that we get out of this optimization. And I'll try to motivate really what this ongoing work is, and that can be something that we can take to the coffee break afterwards as well. So let me just remind you of what the edit distance is. So if you want to change one word into another, well, one way of doing that is that you fix some operations. So that's your first thing that you need to do. And we decide that these operations, if you like, are atomic in some way. So those are the things that we're going to count. And one way of doing this is to say that we can insert a character, delete a character, or substitute. And we'll not go into the details of what data structure we're going to use, but let's just say those are the standard operations that we'll use for that. And if we want to convert the word computer into composer, then we can do that in a number of different ways. One way is that we can substitute the O for U in the word first of all, then we can delete the T, and then we can insert the S. So that's three operations that we can use using those basic operations that we fixed at the top.
But you can also do it with two operations. You can do it with two operations just by doing two substitutions. So the point is, of course, is what is the least number of operations that we need to use for that. So that's been well studied, and you can find that in textbooks on algorithms, and there's a variety of ways to do that. And the thing is we want to find the algorithm that will do the fewest operations, but there's also some more things that we need to start thinking about, what we want to think about, and that is, are all of those operations the same cost? So if we can just say that those are atomic operations, that's fine, but if you think about that, you might need to start thinking about what is the underlying data structure. Again, let's not be too concerned about this, we'll just wave our hands for the moment for these words, but we could decide that that's a contiguous block of memory representing these character strings, or it could be a linked list. So things like insertion and deletion may or may not be a constant time operation. But for the things that we look at, we really do need to fix the data structure. So we need to think about the data structures, but we also need to start asking what are the right operations. Maybe there are some other operations that can work in a better way as well. So our goal is to try to apply those to interaction nets, to these graph rewrite systems. So let me just say quickly what these things are. So interaction nets are a graphical rewrite system. It's a user-defined graph rewrite system. And what that means is just like a term rewriting system where you fix your alphabet of rewrite rules. Here we're going to fix our nodes, the nodes of the graph, and our rewrite rules. So those are going to be user-defined. And the important thing is that our nodes that we're going to use to build the graphs, these nodes have one of the edges, one of the ports of those nodes is what's known as a principal port, and that's where we can communicate with. And that idea of communicating is what's important in the rewrite rules. So the rewrite rules take on this form. We've got two nodes that come together on their principal port. And because every node has exactly one principal port, of course, that means that there's no risk that these two agents here, these two nodes, can't possibly be involved in any other rewrite rule. The idea is that we've got any right-hand side that we want. So it's a user-defined system, so we've got the right-hand side net. The interface must be preserved. So the ports that we've got over on the left here correspond to the ports on the left of the right-hand side. Ports on the right correspond here. And there's at most one rule for each pair of agents. And what we can see by that is that any rewrite that we do can't possibly erase or duplicate any other production that's in the graph. And one of the consequences of that is that you get one-step confluence. So once you've encoded something as an interaction net and you've defined your rewrite rules, the length of your reduction sequence will be the same. In other words, it's going to be equivalent up to. So all reductions are of the same length. So that's the sort of the starting point. It's a very constrained rewriting system, but we can do everything that we want with that. I don't want to go into the details of this example. We'll pick up on a little bit of it afterwards, but this is an example of unary addition, and it corresponds to the addition of 0 and addition with successor that you would normally write as a standard term rewriting system as the definition of addition on unary numbers. And what I want to try to give you a flavor of is that you can write those things down straight away. So here I've got add of 0 and something is the something. So I'm connecting the root here with the x, the free variable, if you like, in that expression. And add, which interacts with the successor, becomes the successor of the add of the two things that we've got there. This is in one-to-one correspondence with the definition of addition, if you were to write it out as the function, as usual functional definition. And there's an example underneath of a rewriting where we've got the 2 add 1, and you do the corresponding reductions using those two things. So this isn't a particularly interesting interaction net because there's no sharing, there's no magical thing going on here in terms of why interaction nets are useful. But the main point that I want to make is that I want to focus on those rules. And the reason I want to focus on those rules is that I want to try to understand, and that's the purpose of this talk, is how do we do those rules in the most efficient way possible. And if we start to think about how do we do that, and we'll focus on one of the rules. So this is one of those rewrite rules. So this is add interacting with successor. There is a line on the top there, but depending on which previewer you use, you get that line or not, but that's beside the point. So let's look at that rewrite rule. So the question we want to ask is, if I want to implement these, this graph rewrite system, these interaction nets, what do I need to do? Well, the first thing that I need to understand is I need a data structure. What's the data structure that's representing these? And every time I do a rewrite, I'm going to do something, I'm going to change something in that data structure to do the corresponding rewrite. And we can kind of think of interaction nets in a way that you cut out the left-hand side, and the left-hand side will always be two nodes of the graph. So you can kind of cut this out of your graph, and the three edges that you've got there will all be plugged on the right-hand side because the rewrite rules have to preserve the interface, and then we just plug this thing here over onto the slide. So we need to think about how we can do this in the most efficient way possible. And the way that we want to get started is to say, well, what is the data structure that we're going to use here? And what are those what are those instructions that we can have? Just like the edit problem, how can we go from insert, delete, and substitute, for instance, which we use for character strings, how can we come up with a set of instructions, atomic instructions, basic instructions, if you like, that can do corresponding graph rewriting? So what we want to do is to convert this thing here into this thing here using the fewest instructions, if you like, that are going to be possible. And not only that, we want to also be thinking about how can we reuse cells. So if we've got nodes in the graph that we can reuse, even potentially reuse by renaming, then we don't need to do memory allocation. And in this particular case, there's two things on the left and two things on the right. We shouldn't actually need to do any memory allocation for this rewrite rule. We should be able to do this rewrite rule in constant space just by doing a few changes. So I'll come back to that example afterwards. But there's also some other things, and that's what I'm going to come up to. I'll come back to right at the very end. When I mentioned this is an ongoing bit of work, the reason why it's an ongoing bit of work is really to do with this order of the rewiring. And I'll say a bit more about that later. So it's not just about the fact what's the right number of instructions that you need to do. It's actually the order of instructions that you do, because that order can have an impact on something else. So we need a data structure and we need some instructions. So what do we need to do to get that started? Well, we've got a number of different implementations. We've been working on this for far too long, but we're still working on it. We've got a number of implementations of interaction nets. The one that actually gives the best performance overall uses one of the most simplest data structures. It's basically a single linked data structure. And the way that we represent nets are basically with, we allocate some memory, which is going to hold the name of the agent, the name of the cell, and pointers, one pointer, we don't need back pointers at all. So these are all going to be tree data structures that we get. And the idea is that we can represent those structures in a relatively straightforward way. This is a data structure corresponding to somewhere partway through computation. What I've got here is the successor of Z, and that's something which is wanting to interact with. So the principal ports, and that's what we've got this thing here, this data structure, which is representing all of the principal ports, to an add of successor of Z and something else, and the something else is then connected to the interface, in other words, the answer under this configuration. And one of the reasons that interaction nets can be implemented in a relatively simple way is that we can have this data structure here. These are what we call the equations. This is all of the active pairs that we've got in the net. So if we've got a net with all of the places where two principal ports are facing each other, those are the red X's. We can put all of those onto this stack, and then we can go through, and each time we do a rewrite rule, we can just look locally, find the new active pairs that are created by that one, stick those on the stack, and keep working. And we don't have to have it as a stack. We can maintain that as a queue, and then there's a number of other things that we can do as well. But the point is, we don't need to search globally for the red X. We can just search locally each time we make a rewrite to see if we've created any.
So once you focus on a regex, then the actual rewriting or replacement, will that be constant time kind of, or not?
Sorry,
so I mean, you focus on some regex and want to do the replacement, no?
Yes.
That operation of replacement. So I have to already
yeah, exactly. So I'm coming to that in a moment.
Just
so
the
actual rewrites is about creating the right-hand side.
Yeah.
So that's a known constant time operation, yes, but potentially a large constant.
Okay.
And we want to get that constant as small as
So
possible.
the rewire, I mean, if you have these like the add zero rule, is that an issue where you just have a line? So
It's no issue at all
It's also
on this.
okay.
Yep, all works. So all of this, of course, so all the things I'm going to tell you now after this slide are all dependent on this particular data structure. But this is the data structure that we've been working with for a while, and it works the best way for us. But it's worth maybe just relevant to this is that you can do several different stacks here for active pairs. So one of the things that you might have noticed when I showed you the add with zero, the right hand, sorry, and with successor, the right hand side had two nodes. That means your net, your graph stays constant size. You do a rewrite, your graph is still at the same size. But there are rewrite rules like add with Z, where your graph becomes smaller. So if we were to maintain different stacks here of rules that will shrink your net, rules that will grow your net, then you can of course decide to prioritize the ones that shrink your net as well, so that you can keep your net smaller. And the reason why that's interesting is that often you find during a graph rewrite, the size of your graph will grow and then it will shrink again. And if you're able to monitor this, you can find that there's a lot of reductions that will keep those things in reasonable place. But that's a side issue from what I want to talk about. Once we've fixed that data structure, we can now fix some instructions. And I won't go through the details of what these are, but these are the things that correspond. These are our bytecodes. These are our basic instructions that are going to build the right-hand side of a net. So they correspond, if you like, to insert, delete, substitute. And what they do is that, so these are, I would say, our basic instructions. They're going to be making an agent. They're going to put a name, rename an agent, and then creating the appropriate wirings that we need on the right-hand side. So we've got some bytecodes that we use. And these bytecodes work on those, not on the data structure that I've just shown you on the previous slide. And we've also got instructions that free up memory cells as well as allocate. So as I say, I won't go into any of the details of that, just to tell you that there are a number of instructions that will do some basic operations. And for each of those instructions, we can draw that data structure, and I can show you what the data structure looks like before and after each of those, so that you can see what's going on. But now if we focus in and look at what's going on with this rewrite rule, then we can start to ask, how do we put those instructions together? How do we know what's the right way to build the right side? And there's several different things to do. So the first thing to say is, well, we can just throw away what we've got. We can just build a new right-hand side. So I can create a new node, call it S, create a new node, call it add, and then do all of the rewiring, and then free up the two old cells that I have, and I get the corresponding code. So that's one thing that I can do. But I can also say, well, hang on a minute, I've got two cells on the left and I've got two cells on the right. Maybe I can try to reuse them. Not only can I reuse them, maybe depending on the order that I reuse them, I might get a better outcome. If I use them in the same, if I use the same agents in the same, so if I use this add here, then I've already got the name, right? But if I'm going to use this as the add on the right-hand side, so this is the memory location that I've got for storing the add, and on the right-hand side, I'm going to have that S. Well, I just need to rename that agent from add to S. So there's a number of different ways that I can do that. And those instructions that I gave you tell you what the costs are of each of those things. So we can do it in different ways. But what we can do is that we can write a little algorithm, and that's where interaction nets start to become not too bad in comparison with usual graph algorithms and also with text replacements. Is because we know we've only got two things on the left. There's only two of the cells over on the right-hand side. So here, if I had 10 cells on the right-hand side, I want to find out what is the best place to position those two things. Now, of course, that becomes expensive the larger the thing on the right-hand side is. But in fact, most interaction nets that we write for the encoding of the programs that we've been testing over many years, we very rarely go over three things on the right-hand side. Most things are nothing, 1, 2, and 3. In fact, occasionally 4. I don't think I've ever seen one that's useful that does 5. So what I'm trying to say there, even though this thing it starts now to, these are NP-hard problems. You've got it's an exponential growth of finding out what is the best place to put all of these things and calculate the cost. Well, in fact, it's not so bad because we've only got two. In this case, we've only got two things to look at, so we can just try the different things. So to summarize what I'm saying here is that we can try what happens where we make add in the first position and add in the second position. We can try to find out what is the least cost from those instructions that I've got before to do that. So we want to find out what's the least number of instructions that I can use and what's the best way of reusing the old cells. So that's basically what goes on behind the scenes. Let me give you a couple of examples so you can get a flavour of what that could look like. So we've got here two different outcomes of what an algorithm could do for generating the code, the sequence of instructions. So this corresponds to the first example that I gave you with the text edits. In other words, that was 3 instructions or 2 to change computer to composer. So here we've got now the left-hand side of the net into the right one. We've got 13 instructions over at the top here, and that's create a new right-hand side of the net and throw the old one away. And the one at the bottom is making good use of the 2 agents that are already there and doing the minimum amount of rewriting. And just to give you a bit of an idea of what's going on here, when I say I'm going to replace now here this add over on the right-hand side, what do I actually need to do? Well, I need to make the principal port of this agent. Well, if we make this add the same as this add here, I've already got that edge the same, so I have nothing to do. Right? So that edge and that edge are already there. So if I'm going to use this one in this place, the first thing I need to do is to update that edge so it points to whatever that thing does over there. So that gives me this edge here. This successor here, which currently points here, means I need to make that point to whatever that needs to point at the left there. So that's my second update. And then I need to do this internal requirement here. So it's finding the least number of instructions necessary to convert the right-hand side. And once we've implemented this, we started to see some interesting gains. It wasn't fantastic in terms of what we were doing before, but it wasn't terrible what we were doing initially. But with this, we started to get some improvements. There's a lot of numbers on here, but the important thing to notice is that we get something like 1.5 times the improvement. So we can improve the improvement factor. Here we go from, so the normal is these are all in seconds, 1 second 43. We've got a lot of different examples that come up with minutes, hours, days for some of these things as well. But the scaling factor is fairly consistent across this. So this is going from 1.43 to 1.11. And that gives you a bit of an idea of the kind of improvements. Here, 1.59, and that comes down to 1. Being able to do those kinds of performances, of course, has an impact overall on different kinds of programs. So these are some example programs that generate thousands, tens of thousands, hundreds of thousands of millions of interactions to do some of these computations. Okay, so that gives you a bit of an idea of the fact that it works at doing something like this. But in fact, what I told you at the beginning is that this is some ongoing work. And in fact, what we're talking about here is just a small part of it, because where it becomes really interesting, if I go back to this table, what this table is showing is the number of threads that we've got. All of our implementations work on with an implementation that makes full use of the cores that we have and the threading capabilities that we have on the underlying process. What does that mean? It means that if we have 4 cores, 8 threads, then we can have an improvement in performance. And this thing has been given us fairly reliable. I'm going to sort of wave my hands a bit, but I'm going to say linear speeder. And that's been something which is quite interesting for the way that interaction nets work. And again, it's because of the fact that one active pair doesn't interfere with another. So any red X's that you have will not interfere. So you can do 2 at the same time, and locally, those things don't interfere with each other. And one of the things with interaction nets is that they do have this local and so-called asynchronous idea of rewriting. But how can we make some improvements here with multi-core? It seems that the more cores that we've got, we sometimes get better improvement, sometimes not as good as we wanted. And in fact, what we really want to think about in terms of a thread-based implementation is when we do these rewrite rules, that I've explained here, there's another thing that's going on. And it's not just how do you do the least amount of work, but how do you do the least amount of work so that you can allow other reductions to start to take place before potentially finish this reduction. What do I mean? I mean, if I'm going to rewrite, so here I've got add and successor, I'm going to rewrite that over here. Well, I'm potentially, when I finish this, I've potentially created two new active pairs. The thing that was connected here and the thing that's connected here, if there happen to be two principal ports at those places. But as soon as I connect this thing here to the output, so as soon as I've created this, before I've done any of the other rewriting, I can already start working on the next interaction. So in other words, I can get more parallelism out of an interaction net rewrite than I can get just by looking at the number of active pairs and the interactions that I've got. But what happens if I do all of the internal rewiring first, and I do this one first, and then I do this one last? Well, then I've waited until I've done all of that. So we've been trying to work out what is the best way to do this in a parallel setting. In other words, how do I do the rewrites so that I can facilitate the maximum number of possible future bits of work that I can do so that I can get a reasonable answer out of this? And unfortunately, what I can report to you is that the obvious things that we can do that should work, it seems to be that we're not getting any improvements at all. And when we've sort of dug into what the process is doing, it seems to there's lots of things going on with the cache. And so there's lots of cache misses that seem to be taking place. And we haven't understood what's going on there. And if anybody's got any good ideas or understands well what's going on graph rewriting and CPUs having problems with the with caching, then I'll be very interested to talk to you at some point. But this basically means that we haven't yet got an idea, and it's still very much ongoing. So it's part of a much larger project to use interaction nets as part of a programming language and as an implementation technique. So we're compiling other languages into interaction nets. We're also using interaction nets as an actual programming language. And a lot of effort has gone into the implementations that we've got. And there's a link here to the implementation. So you can get hold of that and try some of the examples there. But a lot of work has gone into the sort of optimizing those rewrites, how to do the least amount of work on that on those rewrites. And unfortunately, as I've said before, a lot of the implementations, sorry, a lot of the optimizations that we've looked at, unfortunately, didn't give us the expected improvements, and we're still trying to understand that a little bit better. So, incorporating threads, can we find some kind of the equivalent of the edit distance on a graph, which takes into account the threads, is the sort of the theoretical study that needs to do. So that's all from me. Thank you very much.
Thank you.
So in Marc's implementation field is some blocking.
Right. So yeah. So on the thread. So okay. So there is definitely some blocking that needs to be taken place, but there's actually only a bit of blocking that needs to be done. That cell, once you know that cell's involved, then the ports that are involved in that need to be blocked while you finish off the other. So yes, you need to do.
So the result is based on the visible.
So the way that we've so yes, I mean yes.
But as the work and possible to have some block free. Yeah.
So there's going to be some blocking because that any agent that you've got can be connected through an OX. So even though the interaction book is involved, there's an update of the edge that's needed. And the way that we've got these the data structures that we've used, because they're single linked, means that we basically need to mark one place to say, just hold on to this until we're finished. But you can create additional data structures in here to do that. But what we've found is that don't wait is the best way to do it. But what we're also wanting to do, which is part of this, is to try to work out what is the best way in the multi-threaded. So we want to release those blocks as soon as possible. So as soon as you've done that edge, we can say, okay, now we can free up these things so that this agent can now be involved in another one. So how do we enforce it? So we don't enforce anything. An interaction net will, once you've encoded something to an interaction net, there's a given number of active pairs in your original net. So you can find those as you build it. You put those on this stack, and then you just go through that stack. So that's the basic implementation that we use. In other words, you've got a number of active pairs. As you found them, you put them on the stack, and you do them in the order that you found them. Each time you do one, you find again the locally any new ones you've created. You either put them on the front of the stack or the end of the queue, depending on which data structure you're using.
Essentially, have the scheme structure defined, and then update it as.
So in building the graph, you'll identify any red X's that are in there. And once you've identified those red X's, you can decide which order that you want to do those in some way, but it's a one-step confluence system, so it doesn't matter which way you go to do that in terms of overall number of interactions that you're going to do.
And next thing is it not very large. Next
Of
the like itself.
well, the rewriting process is always a constant time operation, the actual rewrite, because we know where the red X is. We don't search for the red X. That's the key point. We never search for the red X. It's always, we always know where it is. And that's really the advantage of this. And the matching problem is we know the names of the two agents. So we just have to say, this is the rewrite route for and 0 or and successor. And we know where it is. We've got a pointer into it.
So your overall view of timings for the different programs, you have a few slides. Yeah, this one. It seems that the speed up's getting slower when you increase the threads. Is that in general?
Yeah, well, we've got this is actually what we've got. This is actually four core, 8 threads, and we've gone up to 9 just to demonstrate what. So yes, it will degenerate.
That's a general effect.
It will degenerate. If you had 16 cores, then you can improve up to that number. But once your cores have run out, then you don't get the benefit.
You would need an unlimited number
Right.
of threads.
But some of the results that we've had, in fact, show some rather bizarre things that it even sometimes slows down on these things, and that's because
that was my question.
and that's
the
the
general
order.
phenomenon was that specific to this example.
Yeah, these were random things that I've put on there, but we're trying to understand that better because when we've tried to do the best thing possible, we've often found that it's not. Sorry,
What are you using for parallelization?
you mean what hardware?
What in software in the library?
It's all written in C. All written in C. Yes, we've actually used a number of different. We've tried a number of different ways. In fact, the implementation that have a look at the implementation that Shinya used, because we've got several different ones, and the one that gives us the best performance is the public one. But we've got some other ones as well. We've used everything going. We've used shared memory, distributed memory, message passing, and objective perspectives.
Okay, I would like to thank Jan again.
I just have a quick announcement because I have to go over the other room. So, dinner tonight, okay? Everyone who signed up for that, we have space for 2 or 3 more. I think 2 are already on the overflow list. We may have space for 1 more. Otherwise, we have to send the email and say join and we have to check it. You want to join as well? Okay, so then we are 20. Right. So anyone else, please send me an email, but we have to check whether there's. So 8 o'clock tonight. Okay. The place is called Alcyon. Alcyon. Can you write something there? Or can you with an email perhaps? Problem is we have a list of everyone on the workshop, but one of them not signed up. So if one of the computers here, you can just show that. So which is the one that is sharing this? It's this one, yes? So I can just maybe.
It's on the opposite of Subway and
which ones?
12 minutes away from there.
Right, so the name of the place, so let me look up the name of the place. This one? Can you see that? No. What do we come? Right. IQ Kitchen. Okay. If you search for that IQ Kitchen, that's where you'll find it. But there's also a map here. I tried to open that in a map. Let's see directions. Don't know if the machine knows where we are. So what does that? Yeah. It's which one? Yeah, selected there. Which one is that? I can't see that. Right, and then directions.
Yeah. Contact the road, please. Yes.
Walking. Oh, can you see that?
Yes.
Well, it's basically, so we are here. You walk out of College Road, your left, and then the next one right, and just down Kings Road. Yeah? If you hit the park, you want the park. This is the big park. This is the university beyond that. Okay. So 8 o'clock. And I think we are fully booked now. Anyone else who wants to join, sort of write me an email as soon as possible, and then I have to check Roy, who did the booking, whether there's any more space. Okay? Cat 2. Cat 2. Cat 2. Right. So
is Caroline? Yeah, it was.
Hey Chris, can you unmute if you hear us?
Hi. Yeah. Can you hear me?
I don't hear you.
I can't hear you.
You can? Good.
Wait just a second. Okay. Try to say something.
Okay.
Oh, not yet.
Do you not hear me?
Yes.
Okay.
Now? Try to speak.
Hi. Can you? Yeah.
Try to say something now.
the Edo thing should be the one.
I have a hard time hearing you guys, but hopefully you can hear me.
Yeah,
We do.
Okay, great.
So
Let me share that.
the third speaker of this session is Kristopher Brown from California. I'm speaking from California, from the University, Stanford University, and he will present the that you see here, the graphical language for that. Please, Chris, you have 25 minutes.
25, good. Thank you. So yeah, I'm going to talk about this graphical language for rewriting protocols. And I'll just start off by trying to say the engineering problem we're trying to tackle. So in general, we're motivated by agent-based models. And here we're using agent, I think, in a different way from the previous talk. In general, we have an understanding of the world where there are types of things, call them agents, and they interact in various ways. And there's not much more in general you can say about them. And these are three motivating examples. And the problem we're trying to solve is how do you represent these models? So whether you're a researcher or a professional engineer, it's important that you can communicate your models to other people, and you can do high-level operations like comparing them or combining them or editing or validating them. And unfortunately, the status quo for representing these types of models is software. So the only formal, despite an engineer or a modeler's rich understanding, conceptual understanding, the formal artifact they leave behind is this piece of code where let's see if I can get my mouse up. So where the agent is sort of defined by a data type in your arbitrary programming language, and the interaction that the agent has is just a function in your programming language. And in general, we have some desired properties of our representation, that it's compositional in certain ways, that we want to be able to verify certain properties and have it be serializable in a programming language agnostic way. And essentially, general purpose code is not a great syntax for these purposes. Whereas these properties do follow, they do tend to follow when we are working in a category that we understand well, such as presheaves or polynomial functors. And we want to give that syntax a semantics that's very similar to this. But by working in a syntax category where you have limits and colimits, we can do these sorts of things compositionally, like combining models or doing these data migrations on presheaf categories in order to do some of these more interesting things. So I think rewrite rules are a great example of this category theory, applied category theory philosophy. They are a good example of this, of replacing general purpose code with a good categorical understanding of what's going on. And it is a good syntax for small or local changes. But the problem we're trying to tackle is, what about some more elaborate simulation that has these rewrite rules as building blocks? And so what we need is some sort of control flow, in addition to having kind of finer grained control over when we order rewrite rules and controlling their matches. And there are some general strategies for this. One is to say, I have a collection of rewrite rules, although I don't have an explicit order on them. By defining certain application conditions, positive or negative, I can effectively control the order of this execution. And sometimes you have to jump through a lot of convoluted hoops in order to make the execution order what you wanted it. And this can be kind of unwieldy. There is a nice syntax that I found in this paper, which has a very nice directed graph. It's very intuitive, and you sort of traverse these arrows. When you are in a box, you apply rewrite rules within that box, and when you successfully apply a rewrite rule, you follow the Y arrow, otherwise you follow the N arrow. And this is nice to satisfy some of the properties we're looking for. The type of control flow you can express is not super expressive, and there still isn't really a good control over matches. And so if you really want complete control, this third strategy is you just have a general programming language that has calls to a rewriting library. So you're going to use general purpose programming in order to structure how you want to execute the rewrite rules. And in general, this is actually a big improvement over just the standard, what I call the status quo, but still, at the end of the day, your representation of your model is some expression tree in some particular programming language rather than a nice mathematical understanding of what the entire model is. And so what we're going to do is we're going to try and find something in between 2 and 3 that has the nice properties of not being a expression tree in a programming language, but also is more expressive than the thing on the left. And we want to understand it as the morphism in some category. Just to introduce, when I show code examples, Algebraic Julia is just a particular library for doing for computational category theory, and catlab.jl really establishes core data structures and algorithms for these co-presheaf categories. So for example, our favorite example is the category of directed multigraphs, which are presheaves on this schema. So we can import catlab and just declare this is sort of the database or presheaf view. And then we can also view with graphviz. And then algebraic rewriting is going to extend catlab with a lot of constructions from graph transformation community, the most basic of which would just be declaring a rewrite rule as a span of 2 morphisms. So this is one that adds a vertex, or sorry, adds a loop to a given vertex. And the very basic feature is that we can just apply that rewrite rule to particular graphs. And you can see it picked an arbitrary match to apply that rule to. So that was the overview. And now I want to introduce what is this category for which a quote unquote agent-based model or a general dynamical system is going to be a morphism in. And I want to focus really on how we apply this to at the end in the case of graph rewriting. So I'm going to gradually introduce the pieces of this category so that we sort of understand why those pieces were necessary. And our starting point is this notion of a Mealy machine. This is a symmetric monomial category where the objects are just sets. in the morphisms, we can also call them dynamic morphisms. Essentially, it's like a function from A to B, except it has its own state space. And when you run the function, it can update its internal state, and then that will change its future behavior. We're going to visualize this using the symmetric monomial structure of a set with the coproduct. So I'm going to represent this function from graph to graph plus graph as a box that has two wires coming out. And really any pure function from A to B is just a special case where the state space is just trivial. So just like that previous rewriting syntax, I'm going to say, well, we can look at rewrite rules as something that has one input and two outputs, where if we successfully apply the rewrite rule, then it will come out the top wire. And if it is not a successful application, in this case, the empty graph would not have a match, then you exit out the bottom wire. And we can also distinguish maybe control flow boxes, which I'll say aren't going to do anything interesting as functions, but they're going to have interesting state spaces perhaps and redirect their input to one of the various outputs. So we could model a for loop with a particular Mealy machine, which has an internal state, which is the natural numbers. And when its internal state is equal to 0, you'll exit out the bottom wire. And when it's not 0, you exit out the top wire, and every single time you run it, the state gets decremented. And so we can combine these together. So this is using this wiring diagram syntax, which is unambiguously parsed as a particular composition of morphisms in this category, and including these braidings and mergings of wires. And this would be, for example, a morphism which behaves like the add loop rewrite rule for the first 3 times you run it, and subsequent times it will behave like the delete vertex rule. And so we're already in a good place, our starting point, because we do have this aspect of we have control flow. We also have some notion of incorporating the rewrite rules. But there are some ways this category is not ideal. One in particular is that our monoidal product, which is the coproduct in set, is not actually the coproduct in this category of Mealy machines. So the reason why is that you could have 2 Mealy machines that have the same behavior, but they are actually distinct Mealy, they're distinct morphisms. And that might be because they have different state spaces. So this shows up in the coproduct because you want this identity to hold, or this identity has to hold for it to be a coproduct. And you can see when we compose this injection morphism with a copair that we're supposed to get out the thing that we copaired. But the problem is this morphism on the left-hand side has a state space which is much bigger because it has this redundant T state space. And that's not really doing anything. It doesn't really affect the behavior because this part will never really impact. But all this goes to show is that what we're really interested in is the real category we're interested in. We care about behaviors, and these Mealy machines are convenient as a syntax, a presentation, let's say, of that behavior. But the real object of mathematical interest is these behaviors. So the sort of next evolution of our category is to be quotienting by behavioral equivalence. So now I'm going to represent our behaviors in terms of these trees. So the way that these trees work is that at every node of the tree, you have an actual function from A to B. And there's a branching at every node for each element in A. So for each element in A, you're going to say, well, the function looks like this currently. And then if I were to run it with this value of A, I'm going to get a new behavior, which is following the arrow to a new behavior tree. Now, this is certainly kind of awkward to visualize when we have infinite sets. When A is the set of all possible graphs, you can't really visualize this. As a special case, which is what I'm going to show in this talk, if it turns out that the actual function on S, the sort of S component of this dynamic update, really, it doesn't depend on the value of A, but rather if our A is this coproduct of values, and when we have like multiple wires in to something, that's like a coproduct. So if the state update only depends on what wire you came in on, then it suffices to draw these branching trees just branching on the number of input wires. And so that's what I'll do here, where this morphism here, which is slightly different from the one before, has two different inputs, and the state updating only depends on what input wire you come in. So I can actually draw it as this binary tree. So when we start out looking at the initial behavior of this, no matter what wire we come in on, it kind of looks like it just behaves like an add loop function. But as soon as we enter through this bottom wire, which if we sort of rotate it, then the bottom wire becomes the right wire, sort of the right branch of the tree as opposed to the left branch. As soon as we enter through the bottom wire, this for loop goes from internal state from 1 to 0, and suddenly now it rewires, and we start seeing the behavior of the function or this morphism is effectively to be like delete vertex if you come in through the bottom and add loop if you come in through the top. So this is just an example of one of these behavior trees. And so now what is this category? Well, there's a few ways of characterizing what these behavior trees are. One interesting one is that they're actually the objects of a particular category, and what category that is sort of depends on these details of polynomial functors and this co-free comonad functor and cat shark, the category of categories and cofunctors. I don't think that getting into a lot of the details of that is actually necessary to communicate the important parts of this paper. The point is that we have, instead of a set of Mealy machines, now we have a set of behavior trees. And although there's a nice co-algebraic representation of these behavior trees, it's going to pay off to actually think about them in this cat-sharp way. Importantly, if we don't just throw away the categorical structure of this category that we send, that all of the morphisms from A to B, if we acknowledge that it actually is a category as opposed to just the set of its objects, so we're no longer talking about a category, but we're talking about an enriched category, enriched in cat-sharp. This is actually really cool because we now have a lot more interesting structure. We can actually have this notion of morphisms between our morphisms in this category. And that actually is really important. So the morphisms going from one dynamical system to another dynamical system are actually the ways that it can update. So I'm going to try to demonstrate that with this example where our system is this composition of phi and psi, and these are the overall behavior. This is the behavior tree for this morphism, and it turns out that any possible way that we update this dynamical system is going to be taking a path in this tree. So a morphism in cat-sharp is where the objects are behavior trees, is to say you start from the root, you take a path, and you end up at another behavior tree, and that is your codomain. And this has some nice compositional properties, like if I have a particular morphism here, let's say I enter in from the top and then the bottom and then the top again, basically we have a universal way of deriving what the updates are for the component parts. So I can update, given an update from the composite to composite prime behavior, I can convert that into, or I know how to derive the update for phi to phi prime and psi to psi prime. So we've essentially made explicit the dynamic structure of our thing. Our morphism is no longer just a static object with a very fixed initial state, but we've made explicit the structure of how it updates. And the very last piece to sort of complete the story is generalizing this morphism not to be this polynomial from ay to by, but to add another polynomial which has a monadic structure. Seeing this in practice might make it clear what's going on, which is that let's say our rewrite rule no longer is going to pick an arbitrary match, but it's actually going to have a list of outputs for all the possible matches. Let's say if it's non-empty, you come out the top wire, and if it's empty, then you still come out the bottom wire. It's unambiguous how to actually apply this twice, which is going to basically add two loops in all possible ways, because we can essentially use the monadic multiplication to then concatenate these lists and now get a list of 9 elements. And this lottery monad, which is very similar to a probability monad, is going to allow us to talk about probabilistic simulations. You might want to explicitly model a probability mass flowing out of all wires, as opposed to having to pick, one wire, or even to do sampling. And so I'll just briefly say that there's this conjectured trace which would license us to use a wiring diagram syntax which has these feedback loops. And this turns out to be a quite difficult thing to prove, but it, importantly, even without that, the theory has already influenced an implementation, and it's already helped us conceptually clarify what kinds of things that we want to support and how to actually implement them in a very generic way, including all of these monadic things. So I'm going to try to demonstrate how our implementation was influenced by this theory by showing how would we sort of run this morphism on some input. Let's say B1 comes in. So the idea is that because we understand our primitive morphisms, let's say our generating morphisms, as these behavior trees, we can, although the behavior trees themselves are infinitely sized, we can lazily expand them. So when I feed in my input to F, let's say F, when it is fed B1 coming in on this bottom wire, it generates a new internal function, and it produces a singleton, let's say, value. And maybe G then takes that value of F of B1, and it now generates A1, A2, A3, and those three values then are fed back into F, which then we expand that tree more. And then let's say each of those values gets fed back into G. So you can see how we can, this is a case of the list monad, but we can essentially be following all these trajectories that are gradually, each individually expanding our behavior trees in memory. And at the end of the day, when we're finished, the simulation, all of our trajectories will have collected at one of the outports. And then we can use the monadic multiplication to essentially then collapse those down. So that's at a very high level how we were able to use this formalism of polynomial functors and behavior trees as an actual implementation for these types of models. But I haven't said yet anything about agent-based modeling or graph rewriting. So the idea is that we want to pick certain morphisms to be primitive morphisms and use those to build up via composition of sequential and parallel and tracing and substitution to actually build up our models from that. So I want to talk about our building blocks in the case of doing graph rewriting and in particular agent-based modeling. So what is this notion of controlling our matches? Because before we had sort of add loop as just this function which picked an arbitrary match. And so you could say that before, when our input was just a graph, the set of graphs really, that the semantics of this box was just to say add a loop to some vertex, no control over which. If we want to add the ability to have distinguished agents, whereby an agent or a focus, I'm going to say, I have a particular map into my graph. So if I have a map from a singleton vertex into a graph, then I have a graph with a distinguished vertex, let's say. And so we can just make sense of this maps into a graph as picking out sub-objects which are distinguished. And we can type our wires via this coslice, objects of this coslice category. So in this case on the bottom where I have add loop, where it says I'm going to add a loop, but I have a notion of a distinguished vertex coming in and a distinguished vertex out, that means that we can think of this as a function for a vertex agent, you might say. And when I come in with a distinguished vertex, what it's going to do is add a loop to that vertex in particular. And what this means is that we do need more data. We do need to say for, let's say we have a DPO rewrite rule, though everything that I'm talking about is general to other semantics for span rewriting. When we have our rewrite rule, we need to also provide data of input agent and how that relates to our pattern. And the control over the rewriting is to say that a match is only valid if it makes this triangle commute. And we also have a notion of an output agent, which might be different. And when we get our resulting map out by, let's say in this case, a push out, we just pre-compose it with this map from B out to R to get our output agent. So, I don't know if this is cut off, if you can't see the schedule or the recipe at the bottom, but this is some algebraic rewriting code which works where we're going to create the delete vertex rule, and we're going to, maybe if I change the aspect ratio, do we still see the screen here? I'm hoping that you can see now this entire recipe here, which is
Yes.
Yeah.
cool. So we are going to create the rewrite rule, but now we need to annotate these rules not only with a name, but also this sort of agent structure. In the case for add loop, all we have to do is say it's a single vertex is the input and the output agent, and it sort of is unambiguous what that means. In the case of this delete vertex thing, we actually are going to explicitly provide the agent in the agent out morphism. In this case, it happens to be the identity on a vertex and the identity on the empty graph. We can essentially use the composition of vertical and parallel composition. Here, we're just going to compose in sequence this add loop morphism, merging wires, and then the delete vertex, and we get something like that. And so now our notion of an agent-based model is this morphism, which can be composed with other ones, and we can actually still run it. We can apply the recipe or the schedule to, let's say, our path graph, where we have a distinguished vertex. Let's say vertex 2 is distinguished. When we apply that schedule, we get two different outputs. The first one comes from successfully applying delete vertex. But because of the dangling condition, we actually can't delete any of these vertices. So we're actually going to exit out the second output. And if we look at the result, you can see that we did add a loop to the second vertex. So
you still have a few minutes, 4 or 5 minutes.
Great, I'm almost wrapped up. So just like we had the rewrite rules, we have also these conditions or control flow boxes, which are not supposed to do anything interesting as functions, but they are supposed to sort of control where you go. And really, these control flow and rule applications are the workhorse generators, and all we need now is a few other things to help facilitate switching our focus from various agents. And a key player here is this query box, which I can define in terms of a Mealy machine or a behavior tree. So it's a perfectly valid generating morphism in this category. But the way it works is that if you come in for the first time, you're going to essentially clear the internal state, and you're going to generate a bunch of you're going to query for all of the B-shaped subagents. And then you're going to run a subroutine for each of those. And every single time you then enter in through this B prime port, you then basically pop off another agent off of the stack. And when you're done with processing all of those, you then exit with your original agent. So just visually, we cannot focus on the code here. Visually, we can see that we're going to come in with no distinguished agent. This box is going to say, do a subroutine for every single vertex. Let's suppose that we add a loop for every single vertex. And then when we're done, we're going to exit out the original with the original agent, which was no distinguished agent in particular. This third output is kind of an edge case where if, let's say we come in with a distinguished vertex and at some point we delete that vertex, for example, we do need some sort of escape hatch for that sort of exceptional condition. And then lastly, these generators I want to show are weaken and fail. They're both stateless generators, and so they're basically pure functions. Weaken converts B agents into A agents via just the data of a morphism from A to B, where you're essentially pre-composing your agent map or your focus. So here we have a distinguished edge, and if we apply this morphism, which maps the source vertex to the source vertex, then you come out with just a distinguished vertex. And then it's also important for us to have an exception state, particularly to give a valid semantics for things that loop infinitely, but you also might, as a modeler, say, well, I don't expect to be in this part of my my program, therefore just throw an error if you end up here. And so I'll just finish by saying that all the examples that I showed, we have implementations for. So we have a game of life example. I don't know if I really don't have time to go through it, but in each of these cases, we have a particular pre-sheaf schema, which is going to represent states of the world. And we represent the basic updates via rewrite rules. And if we were to look at the overall schedule, this might be saying, for every single cell in your game of life, you essentially compute who's alive in the next time step based on who's currently alive. And then we update who's currently alive based on who was flagged to be next. And that is essentially the iterative loop. This wolf sheep demo is also very straightforwardly reproduced by saying for every sheep, we do something, for every wolf, we do something. And what the sheep does is it eats, and then it does some daily routine, which involves moving around and reproducing. It turns out that the wolf does something very similar. And so we can actually use these data migration functors in order to share this schedule, basically to convert this morphism, which is a sheep daily routine, into a wolf daily routine. And really the non-toy example, those are both toy examples. The non-toy example is actually this COVID-19 model, which was a real agent-based model, which is very hard to understand because it's this labyrinth of Python code. And we essentially reproduce that model in this formalism. And this is intended to help scientists communicate with each other and have a better syntax for their models. This is the wolf sheep demo. So yeah, I think I'm out of time, but happy to take any questions.
Thank you very much. Just a technical thing about what you said about traces. You said that it's conjecture that you have traces in that category, but actually you build them. So in a sense, you have a construction which is inspired by the notion of trees, but you didn't prove that they exist. What is the point?
Yeah. So so I can go back to that. So the idea is that formally, for this to have to give this the formal semantics that we want, which is that we want to interpret these wiring diagrams unambiguously as morphisms in this category. We need to provide, we need to show that our conjectured trace operator, which is this involving morphisms of polynomial functors, that we need to show that it satisfies a few laws. But even without showing that it satisfies those laws, we can use our conjectured trace.
Yes. Okay. Okay. Makes sense. Thanks. Question? Okay. If not, I thank you again, Chris. We are a bit late for the coffee break. I'm sorry.
Yeah. Sorry for holding everyone up.
Because of technical problems. And you are early for your breakfast, I guess. Right? I don't know. I think. It's 10 o'clock already. Okay, that's fine.
All right. Thanks, everyone.
I'd say we